Hi everyone, my name is Gergeley TÖRÖK. I am a postdoc in Budapest, Hungary. Last year I was a visiting scholar at Professor Parker's lab in Urbana-Champaign, Illinois, and he offered me the research problem investigating the effect of riparian vegetation on river morphodynamics. Usually the main question in river morphodynamics is what will be the expected equilibrium channel geometry. And this means what will be the width, the depth, and the slope of a given river section. To examine this, it must be known what sets the river geometry. This is true for the river developing in its natural state and for the case where the natural morphodynamic processes are disturbed by an artificial intervention. This is the case on the right, where you can see a dam was installed here, which caused a significant drop in the sediment discharge downstream. Several previous studies have addressed this topic, and they identified what factors play a more important role in river geometry. And these are the bankfull flow discharge, sediment discharge, grain size, skim friction and form drag resistance coefficients, and the bankfull Shields number. This equation expresses the Shields number, and from this it can be seen that holding the slope and the grain size constant, the higher the Shields number, the higher the depth, and thus the narrower the channel. Li et al. Investigated what parameters the Shields number depends on primarily, and it was found that the Shields number can be expressed by a high correlation relationship as a function of the dimensionless grain size and slope. This is shown in figure. The grain line well approximates the trend of the reported values. On the other hand, the measure of scatter is not negligible. For example, the red markers show that the same slope and particle size value pairs can have different Shields numbers, ultimately resulting in various widths. And these suggest the presence of secondary factors. In this presentation, I describe the role of riparian vegetation as a secondary factor in river geometry. The photo on the left shows a small river in Illinois where the vegetation has resulted in a seemingly stable bank. On the right, however, although vegetation has appeared, the eroded river bank suggests instability. Previous studies show that the appearance of riparian vegetation influences the morphodynamic processes of the rivers. An exciting example is the following YouTube video that shows a case in Yellowstone National Park. Briefly, with the appearance of wolves, herbivores have been pushed back. As a result, the riparian vegetation increased, which eventually changed the width of the river. So, vegetation certainly has a role to play in river life, but the impact is not clear. We examined what the presence of vegetation can cause in bank stability. In the case of no vegetation, the weight of the soil contributes to the instability. The frictional force due to the soil cohesion counteracts this. But what happens if the vegetation appears? On the one hand, the vegetation has a certain weight, which also reduces stability. Shearing resistance, however, increases with the appearance of friction between the root and the soil. After all, the question is whether the degree of destabilization caused by the tree's weight or the added stabilization caused by the roots is greater. Based on data from several publications, it can be assumed that in fine-textured soils, the total cohesion, including the added cohesion caused by the root system, is much smaller than in the case of granular soils. This is even more true in saturated soil, which can be assumed for bankfull water stage. From this, however, it can be concluded that vegetation can stabilize the riverbank in granular soils. On the other hand, in the case of fine-textured banks, the increasing weight of vegetation contributes to instability. We intended to verify this conjecture based on reported data. For this, we used datasets of Wilkerson et al. And the one of Parker et al. These datasets cover a wide range of bed grain sizes, but we had no separate data on bank material. And therefore, we assumed that we could approach the near bank material with the reported bed material. Riparian vegetation was categorized based on Hay and Tor classification. According to this, the first class means the case without the trees or bushes. The second class means 1 to 5% tree or shrub cover. And the third class means 5 to 50% cover. The fourth class refers to the densest vegetation. The variable V then refers the degree of vegetation cover. This figure shows 176 river points with different colors according to the vegetation classification. The green line shows the relation of Li et al. Estimating the Shields number. It can be seen that the points follow the trend well. But can the vegetation explain the scatter of the points? This figure shows the ratio of reported and estimated Shields numbers, and the horizontal axis shows the dimensionless grain size. The scatter could be examined on this basis. We calculated the ratios average separately for each classes and separately for sand and gravel sizes. The first shrinking phenomenon is the proportions depends in reverse on the density of the vegetation. In case of coarser material, if the coverage increases, the Shields number also increases. It follows that the width decreases. In contrast, in the finer material, the denser the vegetation, the smaller the Shields number, and consequently the wider the riverbed. Differences in ratio are also examined. Differences between classes show that the scatter is stronger in the case of sand than in gravel. We didn't know the riparian vegetation's type regarding the reported river sections, which also left us without knowledge of the root's depth. Based on Fox's et al. Publication, however, we assumed an average root zone depth of 3.3 meters. The figure's vertical axis shows the value of the bankfull water depth normalized to the depth of the average root zone depth. The horizontal axis shows the ratio of reported and estimated Shields numbers. The coloring indicates vegetation coverage. Red lines show coverage above 50% and orange lines below 5%. Furthermore, solid lines refer to granular soils and the dashed lines to fine textured soils. The figure shows that up to the root zone depth, the Shields number depends on the vegetation cover according to the behavior presented earlier. That is, in sandy, fine-textured soils, it decreases as the vegetation grows. In the case of gravel, it increases. In a decreasing degree, this regularity is correct roughly to the bottom of the root zone, but not after that. Finally, we attempted to improve the relation of Li et al. By considering riparian vegetation. We fitted exponential functions to the reported and estimated values, value ratios separately for the four classes. Thus, more accurate shields number can be estimated by considering the table's values for the corresponding category. We calculated the mean ratios of the reported and estimated shields numbers separately for each class. It can be seen from the results that the modified estimation has indeed brought a substantial improvement. Based on a trend analysis of the different classes points, we suspect that riparian vegetation is a more decisive secondary factor in river morphodynamics in granular banks. In the case of cohesive banks, other secondary factors presumably play a larger role in river morphodynamics than vegetation, which probably explains the scatter here. Our study's most important message is the reversal in the trend of shields number with grain size as we go from cohesive to granular soils. It follows that in the case of cohesive soils, the denser the riparian vegetation, the wider the bed. In the case of granular soils, the opposite dynamics can be seen. Finally, I want to sum up with emphasizing the main outcome, and this is that increasing the vegetation density tends to make rivers with a granular bank basis narrower, whereas increasing vegetation density tends to make rivers with cohesive bank bases wider. Thank you for your attention.